AP exam, and because of that, I want to make sure we're really zoned in and focused on it. So quickly answer these for me. Saturated solutions are when ions and solids are at dynamic equilibrium, right? The word of the day, dynamic equilibrium. And so how do we represent that in a BCE? We go solids equilibrate to ions. And so it depends on the favorability of the ion formation, but it can be lesser or more than, or the K value can be lesser or more than 1. So when you're looking at, and my board is really awful right now. When you're looking at those values, which one of those is definitely the least soluble? Cadmium sulfide, why? Okay, so the smallest KSP value. So why am I able to compare these? There's something specific about the 4 that I've selected. Yeah, like
they have the same ion-to-ion ratio?
Right, so you'll see this is 1 ion, 2 ions. So each of these has 2 ions. So that's the only reason I'm allowed to compare their KSP values. If I had like sodium sulfate, I would not be able to compare that one relatively because it has how many ions? 3, where all of these has an ion factor of 2. So I can compare these. So why is this value so small? What makes it that small? Mathematically, how do we calculate K? So product concentration of a reactants, it is rate of array, but we're talking equilibrium more on this one. So it's products of reactants, right? So what value makes that so incredibly small? Well, reactants in this case are what state of matter? Solids. Are solids included in Ks? No. So it can't be the amount of solid. Who cares about solids? They're not relevant for K at all. So it must be the number of products, right? So this value is so itty bitty because the product ions are really tiny. Well, let's say this makes X and X amount of cadmium 2 plus and sulfide 2 minus. X times X gives me KSP, right? So what would approximately what would X value be if we know that X squared is equal to this? Something times 10 to the
like 6.4 times 10 to the
13, 14, right? Something really tiny. So I'm just basically saying the square root of 10 to the negative 27th is we cut the exponent in half. So something really small. And so that indicates you'd be like, yeah, it totally makes very, very, very few ions. Okay, so we already answered this one. Relative solubility compared must be with the same ion-to-ion ratio. Thank you, Clayton. Solubility changes with a couple of things. Give me 2 factors. Temperature and pH. Good. We're going to talk about the pH one more specifically. What does just the general term solubility mean, and what units might be used to represent it? Solubility. Anybody?
3 grams in 100 milliliters.
So we can say grams, and a lot of times we do say milliliters of water, but in this case you'll actually see it grams per liter, or you'll see it as molar solubility as moles per liter, right? Molar solubility is just simply molarity. That's the amount of solute dissolved in solvent. So it's just using those terminology, those terms. What are conditions? What are the conditions of solution when K does not equal KSP? So let's first talk about what is true when K, SP, and Q are equal. When they are equal, what kind of solution is it? Saturated. So we're at this point, we're starting to specialize our equilibrium. So we just did general equilibrium. Now we're talking about equilibrium in the aspect of precipitations and saturated, supersaturated, and unsaturated solutions. Next unit, we're talking about equilibrium in reference to acids and bases and so forth. After that, we'll do buffers. So equilibrium is a big, huge topic, and there's all these specialty topics we talk about within it. So KSP equal to Q is saturation point. So when Q is less than KSP, talk me through this. Why is it less than KSP? What's causing the Q to be lower than KSP?
There are not enough ions in the solution.
Okay, that is the simple logic. That's all I really need. Is I don't have enough ions in solution. So if I know I want to make more ions to get Q up to KSP, too few ions would mean that it's an unsaturated solution. Does that make sense? Too few ions unsaturated, and then opposite, Q is greater than KSP would mean too many ions. So what kind of solution? Supersaturated. I'm not going to show my cat video or my bear video. Polar. Like this, I was like non-polar. Who remembers my polar bear video? Thank you. Okay, jeez. Okay. So what is the common ion effect? Common ion effect? Anybody? All right, let me tell you, there is a common ion involved. What common ion to what? Like what's the word common really referring to? You guys are like, this was on the web quest. It's what? This is an ion that's present in the equilibrium BCE. Okay, so it's an ion common to the BCE. And so you add something that's common to it, it's actually going to change the solubility because it shifts the equilibrium in one direction or another. And we'll get into more details about that momentarily. pH can also play a role because it can, guess what, change the solubility. And it's doing that because it shifts the equilibrium a little bit as well. So we'll talk about it consuming and combining with different things. Number 9, this looks kind of complicated, but I want you to kind of give me your most honors chem answer possible, not AP right now. So if you're basically trying to figure out which ion will precipitate first as cadmium and nickel ions are added to a sulfide, something with sulfide in it, a solution with sulfide in it, which is going to precipitate first? So what's your gut instinct here?
Cadmium.
Why cadmium?
It's the least likely to form solution.
Right, so I can have very, I can keep going, very few cadmium ions and sulfide ions in solution together because the Ksp value is so tiny. So once I start adding so much cadmium or so much sulfide, it's going to start to combine together and start to form a precipitate because I just have too many atoms in solution. I can relatively combine or add more nickel and sulfide together because their Ksp value is bigger so that they can accommodate more ions in that saturated solution. So they're not going to precipitate until far after the cadmium starts to precipitate, simply because the Ksp value for this one is so small. So I thought your gut instinct would have been cadmium, but we'll get into selective precipitation momentarily. All right, so let's watch a video first, and this is going to explain from a big perspective of solubility down to Ksps, and then we'll actually do some problems together. Because the problems are not hard, they're just different. I can't remember my Pandora password. Let's apply this. Okay. So it's a 7-minute video. Let's write down 7 things. 1 thing a minute, okay? Write it on your warm-up.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 70. It's on solubility. You've probably noticed that if we add salt to water, it will dissolve. But if we add more salt and more salt and more salt, eventually it doesn't dissolve anymore. And so what's going on? Well, if we look down at the atomic level, we're adding a salt grain, and that's made up of all these ionic bonds, sodium and chloride, and they're going to break apart into their aqueous ions. They're going to be ushered away by the water. That's going to increase the concentration of those ions in solution. And so if we increase the amount of ions, eventually no more ions can be added. And so that's going to push it back to this more solid form of salt. And so if we look at a solution, remember, we're dissolving a solute in a solvent. And so you can think of that solute as a solid if it's all chemically bonded together. And if we can break it apart into its ions, then it's dissolved in solution. And so if we think of on the left side of our equation, we have the solid form, and on the right side, we have it broken apart into its ions. And so really in a solution, we have a reversible reaction. It's going to have its own equilibrium constant, and we'll call that Ksp, which is essentially the solubility product constant. And that's a way to measure the solubility of any kind of a salt. And so there are a few things that are going to affect the solubility. One of the big ones is going to be delta G. In other words, it's going to be the enthalpy, it's going to be the entropy of the system. Let's say that there are really intense bonds between these in the solid form. It's going to be hard for those to break apart into their ions. Likewise, as we change what is in the solvent, if we add more ions to it, it's harder for more ions to be added. We could also change the pH, and that's going to affect what can be dissolved as well. Now, there are a few things that dissolve readily in water that you should simply know. Those are going to be the ammonium ions, potassium ions, sodium ions, and then also the nitrate anion as well. And so if we look at sodium chloride breaking down in water as a reversible reaction, on the left side we're going to have the solid form, on the right side we're going to have the two ions that are in aqueous environment. Remember, we're breaking those apart. A wonderful simulation to look at this is the PHET on salts and solubility. And so I'll put a link down below, but basically I'm going to add a little bit of salt, and we're going to look at this at the atomic level. And so what's going to happen is the water's ushering those ions away, and so we're going to break it apart into its cation and its anion. Let's say I radically increase the number of ions. What's going to happen? Well, you can see that most of them are going to be in solution, but some are going to go back to that solid form. There's simply too many ions out there. And so we've pushed it.
Oops. So if it's too many ions in solution, what happens? What is the relationship between Q and K? Q is greater, right? And so you can see it's shifting back which way, or proceeding back which way. So the reactant side, the left side, which is solid, and you can see it's starting to clump together. And he also mentioned the entropy versus enthalpy. We already knew a little bit of this when we talked about our hand warmer lab. You talked about like why it's something dissolving, why is it not. When the bonds are really strong between ionic salts, it sometimes links this solution. Someone? Okay. Yeah. Can you tell me something about it? Or should we do it right now? Okay, thank you. That's a useful. Okay, so whenever ionic salts are really strongly bound together, they are less likely to dissolve. So think back to your solubility rules. What are some really very insoluble products, insoluble ionic compounds? Things with what kind of anions? Sulfides. It's CHOPs, right? So C is carbonates, hydroxides, oxides, phosphates, right? Phosphates is the one I'm going to really want to focus on because the strength of the ionic bond is depending upon the charge of those ions. So aluminum phosphate, what's the charge of aluminum? 3. Charge of phosphate? 3. And if you multiply their charges together, that tells you the strength of their bond. So multiply their charges, what do you get? 9. A 9 strength is much, much, much stronger than sodium chloride's bond strength. What's that? 1, because it's 1 plus times a 1 minus, that's 1. So the reason why we have these solubility rules, it's really based on the charges, because it's Coulombic attraction, it's the attraction for one another. So a 3 plus and a 3 minus have a really strong attraction, whereas a 1 plus and a 1 minus have a lesser strong attraction. And so that's actually why we have solubility rules. They're based off charges, they're based off the solubility products as well.
More towards the right side of this reversible reaction. Now let's look at a different salt. So now we've got silver bromide. If I were to add 200 of the cations to this, we're going to see a different kind of an effect. What's happening is that they're all going back to that solid form. So if we were to look at this equation up here, it's shifting it back more towards the left. And so how do we measure, does a reaction go to the right or does it go to the left? Remember, that's going to be our equilibrium constant. And so if we look at the equilibrium constant of sodium chloride being dissolved in water, we could set it up like this, where it's going to be the concentration, remember, of the two products over the concentration of that reactant. Now we can get rid of that reactant since it's a solid, so our Ksp value is going to be 37.3. What does that mean? Since it's much greater than 1, that's going to shift it way towards the right. We're going to have way more of those ions. If we compare that to the silver bromide, what's our Ksp value here? It's going to be much less than 1. What does that mean? Our equation is going to be shifted way towards the left, and so we're going to have more of that solid form. And so the neat thing about this simulation is you can play around with the Ksp values. Now I've got a theoretical salt with cations and anions, and I'm simply going to lower the Ksp value. You can see as I lower it, it's starting to move back more towards the left. It's moving back more towards that solid form. So if you have a really low Ksp value, it's going to be shifted towards the left. If I radically increase Ksp, then it goes way back more towards the right, or in aqueous solution. And so that's what Ksp affects, but you should be thinking, like, why does it affect that? What affects Ksp? Well, it's mostly going to be delta G, so changes in enthalpy and changes in entropy. And so if we look at the solid form, remember there are going to be ionic bonds between all of these, and the greater those bonds are, it's harder to break them apart and then move it away into solution. And so also there are going to be interactions. Once it does get broken away, it's going to interact with the solvent itself. And let's say there are already a lot of ions in solution, it's harder to be added. And we could also change, for example, the pH of that solution increase or decrease the number of protons, and that's also going to change how it interacts with the solvent. Now, we basically just talked about enthalpy. Remember, entropy is going to be an important part of this as well, and that's why it's better to look at the whole delta G. And so what are some applications of this? Well, let's say we have seawater and fresh water, and we're going to try to dissolve salts in each of those. It's going to be different, because in seawater, we're going to have all of these ions already present. Sodium, chloride, sulfate, magnesium, all of these are already there, and so it's hard for us to add more of those salts into solution. What's another application of this? Acid mine drainage. So how did this get so nasty? Well, there was probably a coal mine at some point that had a lot of sulfur in it, which combined with water and made sulfuric acid. And as it drained through this area, that decreased the pH, and so there's all of a sudden a lot of ions in solution, mostly iron hydroxide. What happens as it's now settled out is we're adding more fresh water to it. It's increasing the pH at this point. We can't hold those in solution, and now all of these ions, all this nasty iron is coming out of solution. Or we could look at acid rain. What's happening there is we're decreasing the pH, and that changes the amount of carbonate that we can actually dissolve. And so did you learn to predict the solubility of a salt or rank its solubility given the KSP values?
All right, so I like to show these because they have good applications on there, and the College Board loves to add a specific question related to any application, because chemistry is very applicable. If you take ACE next year, you'll learn about this as well. They talk about environmental causes and the influences of chemistry, like environmental chemistry. So this right here, this is on your notes. Let's quickly review this, and then before we do, I'm going to start with a question. I'm going to start with a question. Let's see where we are, because some of this is just reading, which you have already done, and we've discussed further. Look at question 1 on, I'm not sure what page it is, exercise 1. I'm going to start us with an example, and we'll move back if needed. So whenever we do an equilibrium question regarding KSP, first of all, what does this SP stand for? Solubility product, because it's a product of the ions that are soluble, right? So that's why the SP part makes sense. So we have copper 1 bromide. It's telling us that the solubility is blah 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 moles per liter. And I will tell you up front, anytime you see the solubility, a lot of times, most of the time it's given as molar solubility because it's given as moles per liter. And a lot of times the solubility number is X. Okay, so right is X, reserve on exclamation point, whatever. That is most of the time X. And so if you're ever like, what the heck do I do with this number? Let's see if it's going to serve that purpose of X. Okay, so copper 1 bromide has a measured solubility of blah at 25 degrees C. The 25 degrees C is just a standard condition always given. It's not really important right here. Calculate its KSP value. Okay, so its KSP value is going to be based off, first you writing its BCE and expression. So what is the BCE for the dissolution of copper 1 bromide? Start me off. It's always the same theme, the way it looks. CuBr, solid. Okay, I need you to write your states of matter here. Equilibrates in water to Cu1 plus and Br1 minus. And leave yourself space underneath it because you might want to, use your BCE as the beginning of your ice box or rice box, or whatever you want to call it, okay? So if I'm telling you copper 1 bromide is soluble to 2.0 times 10 to the 94th moles per liter, that right here, yeah, it does talk about copper 1 bromide, but that's not the important part. It's saying that it makes 1-to-1 mole ratio of both of its ions. So if it's that soluble in water, it's going to make that amount of each of its ions. So that, like I said, is X. And so I'll show you what I mean by that. Whenever this dissolves, it's making, whenever this is dissolving, you have a number here originally. And I'm just going to put that there because it doesn't matter what the number is because it's a solid, it's irrelevant. Whenever this dissolves, a small portion will dissolve. So I'm subtracting a small portion, right? It's going to make a small portion of the other two. Where I start off at 0 for the products, I'm making X and X amounts of both of these. So, but it will always be this way. You will always start off with 0 products. You will always have a solid that is irrelevant. So most of the time in our ice boxes on KSPs, I just write ice next to it, and then I put an X. Oh, I put a scribble, because I don't want you to think that's an X. I put a scribble through the solids, and I just say I make X and X amounts of those. So this is my simplified ice box regarding the BC above. Okay? So I'm making X and X amounts of those. Well, this is X, right? So let's set up our KSP expression, because I haven't done that yet. What's our KSP expression? So ion concentration of copper 1 and bromine or bromide to the first and first power. So guess what? Those are x times x, which is just x squared, which is number squared. 2.01 times 10 to the negative fourth molar squared. So that's what? 4 times 10 to the negative eighth. Is that right? 4.0 times 10 to the negative eighth. That's how you get KSP. Some of them are very easy. Let me double check that answer there. And I've typed out these, or I had these questions printed for you, so I'm expecting.
That's right.
Thank you. You guys to have it on your. It's on your NSMI thing too. The answers are okay. So first step, write BC. Second step, find your or do your expression. Third step, plug information in, and that information was given to us very readily. Questions on number 1 right now? Cool. Okay, let's do number 2. Calculating solubility again, but this one's a bit more complex. I did a 1-to-1 mole ratio for the first one. Chelsea, I'll go back to it later for you, okay? I want you guys to tell me the BC for this one first. Or bismuth sulfide. Bismuth 3 sulfide.
Solid.
I don't know what that is. BI2S3 solid equilibriates to 2 bismuth what? 3 plus and
Plus 3 sulfide.
2 minus. Okay, so we can see the ions formed are just uncrossing the charges. So what is this K expression?
Yeah, that's good.
So bismuth 3 plus squared and
That's good.
okay. So make sure you set up your information with your charges and with your exponents. Okay, so how much of each of these products do I make in terms of x's? How many? So I know the solubility is 1.0 times 10 to the negative 15th, and that's telling me how much of this dissolves. But when that dissolves, it doesn't make a 1-to-1 mole ratio both of its ions. It makes multiple of both. So it's going to make more sulfide ions as compared to bismuth because of the ratio. So we have to put that in perspective of x at first. Okay, so how many x's of bismuth does it make? 2 x's because it's starting off at 0. It's plusing 2 x's at the equilibrium. It is 2x. Do you see? I'm just skipping the initial and the change. Okay, so this is ice, and this is scratched out because it's a solid. Nobody cares. How many x's of this sulfur does it make, or sulfide? 3x. Okay, so these x's are going to become what's put in here, and since we know x is this right here for its solubility, we can plug it in. But I'm going to plug it in at the very end after we simplify our math. So KSP is equal to 2x squared. So I'm just plugging in what I put up under ice in here. 3x cubed. All right, here's where the math comes in. How do I simplify these things? So give me our exponents and tell me what mathematically 2 squared is. 4. What's 3 to the third? Not 9. 27, right? That's where you have to go. 3 times 3 is 9, times 3 is 27. So what have I just done? I've just did 4, and then x is still squared, and then 3 to the third power is 27, x to the third, because it just transfers in, right? So then 4 times 27 is 108? No. Yeah, 108? Is that right? Yeah, okay. Is that right?
Yeah.
Okay. I have to double check like 5 times. And then whenever you combine like terms, what's your x? X to the fifth. All right, so on your on some of your math work, on your quizzes, it's beneficial to you, Anthony, to don't just stop here, because I know you can plug in x, but you might accidentally forget a squared or a number someplace or parentheses. It's good to go ahead and try to get down as simple as possible so you can plug in one number. So here, I'm going to do this number for x. So then 108 times 1.0 times 10 to the negative 15th molar to the 5th power is going to be my KSP value. What is that? that value, guys?
1.08 times 10.
Okay, this is KSP. So what can you imagine about bismuth 3 sulfide? Very insoluble. So in water, it would probably be a solid, and you would, I mean, there would be so few ions it wouldn't even exist really. Okay, so that was a little bit more complicated. Let's go to this one. This one has to deal, this one actually just a slightly different way to represent solubility in terms of moles per liter versus grams per liter. So I'm just going to kind of show you how to do this one at first. If I have the KSP given to us, that's not what we're solving for, right? So what do you think we would be solving for in a case like this? So in the previous examples, what did I give you? So I gave you solubility, so I gave you X, right? And we solve for KSP. So if I'm giving you KSP, what do you think we're solving for? X, aka the solubility, right? So what's the KSP expression for the dissolution of this thing, calcium carbonate? What's the expression?
Calcium.
Ion, okay, times carbonate, and those are both a 1-to-1 ratio when they dissolve, right? So that's why the exponents are 1. So when I make them, I make equal quantities of each of them. So I get to call that X and X. So I'm making X and X of both. So my KSP, which is given 3.8 times 10 to the negative 9th, is equal to what in terms of X's? X squared, because I'm making equal amounts of this and this in solution. So this is X squared. So then how would you solve for X? Square root X is equal to something 6 point something times 10 to the negative 4th. That value 6.16 times 10 to the negative 5th. Okay. And what unit is that? Molar, right? So moles per liter. So that's molar, aka moles per liter. How would I convert that to gram solubility? How would I change that to grams per liter? Multiply it by what?
To do the molar mass.
Molar mass. Okay, so this is a slightly different one. 10 to the negative 5th moles of what? Calcium carbonate. Okay, so it's just recognizing what each of these values or terms are pertaining to. So if I wanted to convert that to from moles to grams, I'm just going to then implement using the molar mass. Calcium carbonate was 100 grams. So one mole of calcium carbonate weighs 100 grams of calcium carbonate. So then the solubility in grams per liter would be 6.16 times 10 to the negative 3rd grams per liter. So it's a different way of expressing it. How are we doing so far, guys? These are the easy ones. These are the ones where it's just ice, number is given, solve for the one that's not. So we're going to start mixing things together now in terms of common ion effect, mixing different types of solutions and stuff like that. So this, tell me how you'd set this one up, and then I'll probably leave this one alone. How would you set that up? When it says calculate the solubility, what is it asking for? It's asking for X, so how would you solve for X? So KSP is equal to,
Concentration of copper.
I'll just write it out what you're saying. KSP is equal to concentration of copper 2 and iodate
-1
squared, because it's making 2 iodates in that dissolution. So then what X's would be going in here?
X into X.
X and 2X squared. Don't forget. So that's what I like to write the BC. Sometimes we skimp on that, but I don't want you to just trust your brain all the time. I want you to prove it to yourself. So there's copper, and then there's 2 iodates, and so that's going to make 2 X's. That's why 2X goes in here. But some of us can just go straight to the chase and get it done. Simplify that for me. So 2 squared is 4x cubed. Math 2, math 1, don't remember. Math 1 1/2, I don't know. So 4x cubed. So then from there, you could then set it equal to the KSP value given, mathematically then divide by 4 and then cube root it, and you would find the x value. Okie dokie? Math. These are dead to me right now. Why are you dead? Don't be dead. This is like, I love KSP. It's good stuff. Alright, this is the common ion effect one. Okay, so this is one where we have to set up an icebox and we have to implement some initial information. So we have calcium fluoride. I have the KSP value given. I'm calculating the solubility. What am I solving for? Calculating solubility. Again, I'm looking for X. So I usually write that up there so I just don't forget that I know what I'm looking for. But I actually already have an initial given. I have sodium fluoride that my solution is actually made of. So it means I have a common ion in this reaction already. Which is the common ion? Fluoride ion, right? So let's write out the EBC, or the equilibrium reaction. What's the equilibrium reaction? I'm dealing with calcium fluoride.
Calcium fluoride solid.
Calcium fluoride solid equilibrates to
Calcium 2 plus.
calcium 2 plus and
2 fluoride.
2 fluorides. Okay, so here at this point, I'm going to write out ice actually versus ice by simplification. So how much initially do I have of everything? So I don't really care about the solid, right? So I'm just going to go like this for solid, just for that purpose. What do I have of the calcium? 2 plus. 0, because it doesn't say I have any. What do I have of fluorine or fluoride? Right, so this right here is telling me that I have 0.025 molar of both 2 ions, sodium ion and fluorine ion. These are initials, but the sodium is irrelevant. It's the fluorine that's important, and it's just because I make a 1-to-1 ratio of both of those. So that is my initial, 0.025 molar of the fluorine. I do not multiply by 2. That 2 right there is distracting. It's not there for the sodium fluoride, it's there for the calcium fluoride. So now I actually have an initial, so I have to do some more math. So as I make calcium fluoride, calcium and fluorine, how much of each do I make? What's my change is what I'm asking? I'm adding 1x here because of the 1 here, and
2x.
I'm adding 2x here. And why am I proceeding right to begin with? Because you don't have any calcium, you have calcium fluoride, it's got to make more product. So I have, in the end, x here, and then 0.025 plus 2x here. Okay, so again, I'm solving for x. So what else do I need to set up right now? What do I need to set up? KSP expression. So I'm trying to really be diligent about how I use the term. So KSP expression just means to write out the products over the reactants. In this case, it's just products. KSP is calcium ion times fluorine squared. Okay, and then what am I plugging in? X and don't forget about the common ion, 0.025 plus 2x squared. And this KSP value is given to us as 4.0 times 10 to the negative 11. Okay, so tell me what that KSP value is really telling me. What's favored? Okay, this is a low KSP value, right? So reactants are highly favored, meaning the solid form is highly favored, right? So we know it's not going to be a very big number of x's that are added, but I don't know if it's negligible or not. So we can try to neglect x and see if we can neglect, but you have to prove it to me with the 5% rule, or you can actually, at this point, plug it in your solver and go. But I'm going to try to neglect x to prove to you that you can do it with these types of problems too. But I'm only going to be able to neglect the x that is added to, or subtracted from a true number, not 0. So then when you simplify this, you get x times 0.025 squared is equal to 4.0 times 10 to the negative 11. So square that, divide, x is a number such as 6.4 times 10 to the negative 8th molar. So if x is that, is it negligible? Totally, like 10 to the negative 8th versus 2.5 times 10 to the negative 2nd. There's a definite, there's more than 5%, it's like 0.0005, something like that. And I don't have a value right here, but I'll write it over here for purposes of showing you what we're doing here. 6.4 times 10 to the negative 8. You guys have your calculators. Somebody do this from your class. That divided by the number we were going to subtract it from times 100. This is like, can I neglect X? 10 to the negative 4%, right? Did you multiply? Okay, good. So that's definitely less than 5%, so yeah, you can totally neglect. Okay, so what did we just solve for? X, which is the solubility of the calcium fluoride, right? Tell me, knowing kind of what we've set up here, this is the amount of calcium fluoride that dissolves in a solution of sodium fluoride. Do you think this number would be greater, lesser, or the same as if calcium fluoride were dissolving just in water? Different how, up or down? Is this number smaller or greater than just calcium fluoride dissolved in water? Why is it smaller?
Because there's already common ions in the water, so there's already ions there.
So can you explain that via Le Chatelier's principle? Okay, so this is smaller than calcium fluoride in water because of the common ion effect. And the reason that works is because, like you said, there's already products in solution. So you're not going to shift as far to the right because there's already product kind of as a barrier. So it's going to limit the amount of product made. So because fluorine, I'm going to say just the concentration of fluorine present shifts somewhat to the left. So that's why it's basically limiting the amount of ions that can be made because there's already ions present. That's just called the common ion effect. And you can use that, I think, in your, I don't remember which part of your lab it was. I have to look, but I think it was probably present in one of your lab questions. Okay, take a stretch break for me. Get up for me. We have like 3 more problems to solve together. Two more. Oh, I'm so excited about ugly Christmas sweater. Ugly holiday sweater. Holiday sweater. Tomorrow. Is anybody excited? Is anybody planning on wearing ugly sweaters? Yeah?
You can bring us in.
I made one last year because I didn't have one and I felt like buying one. So
Well, I have 2. Because we have the holiday sweater competition for the teachers next Tuesday, so I'm not going to wear tomorrow. I have a chemistry
like
one.
a better one for the contest.
I know, but I could always wear it twice. Like I don't wear mine wearing Thursday and then Tuesday, just for science. But I also have superhero ones.
Oh, didn't you just buy it?
The holiday one? I sent it to you guys on Silly.
Yeah.
Yes, that's what I bought. My husband's like, did you seriously buy this for like $25 or $30? I was like, yeah, I did. Christmas present to me. Okay. We went over that. I'll show you this first. Okay, bear with me. If you need another stretch break, let me know. I have to talk more today than normal. So this I printed for you, yes? This is on your sheet someplace. Please tell me yes. Okay, good. This is kind of what the warm-up, the video was regarding with saturated, supersaturated, and unsaturated. But I want you to put it here because you're going to forget the theme of Ksp. What does Q greater or less than K mean? So again, why would Q be greater than K? I'm starting on the bottom one. Why? They answered me earlier on this one. Huh? Too many ions. Okay. So too many ions in solution means that it is a supersaturated solution, right? Well, supersaturated solutions are very fragile. They're very unstable. They will immediately precipitate out. And the reason why, though, is simply because when you have too many ions in solution, you must proceed left, right? So if you must proceed left, what are you making? Ions or solid? Solid. And that's because of this just generic equation or equilibrium equation for anything that's Ksp related. So when you proceed left, a precipitate will form 100%. So if there's ever a question, it's like, hey, will a precipitate form? You're probably going to have to calculate Q. If Q is greater than K, then you're like, yes, a precipitate forms because reference the Q number, reference the K number, and that's enough support for AP questions. If it's unsaturated, that's because there's too few ions in solution, so too few ions means you must proceed which way?
Right.
Right? And so will it precipitate form?
No.
No. So, because you're making more ions, not more solid. So, like I said, if it's ever asking for if a precipitate will form, it's that forces you to look for Q. And if Q is less than K, then you would say, no, precipitate will not form because Q value is X, KSP value is Y, and that's showing your compare. So anytime they ask you to compare, do show both values. So this was called the reaction quotient again. So if it acts for reaction quotient, that's what K is, that's what Q is referring to. This last part here is giving us a bit more information on like, okay, once I start proceeding left or right, when does it stop? It doesn't just go until the end. It's going to stop when K and Q are equal to one another, meaning it's going to stop shifting once at saturation. And that's why saturated solutions are very stable, because they are at their equilibrium position. And so this relates back to, you know, our supersaturated ideas, and then also solubility curves. And you might remember solubility curves a little bit from honors. If it's on the line, it's saturated. If it's above the line, it's supersaturated. If it's below the line, it's unsaturated. So you can graphically get this information and plug it into a KSP value as well. Almost every single APFRQ question has a diagram, a graph, a chart, a picture, something with it. So I don't know what they're going to throw in this year, but I'll see what I can find out. Know people can know people. I know one person who's a grader, and they told me some really good information. Like, I did not realize you get points taken off for putting, like, okay, seriously, if you put a KSP, you know, with products over reactants, well, the reactants are solids, right? Solids, if you put over 1, you get 0 credit for the expression. So, like, what I'm saying is, don't even put product, don't even put it over 1. I know 1 is fine mathematically, but they said that if you put it over 1, you're saying that the solids matter. I was like, I didn't know that. I was letting people do that for like 5 years. So anyway, don't put it over 1. Okay, so these types of questions, I'm going to scroll down here first. You'll see that it's a little bit more complicated because I'm giving you 2 reactants. And if you look closely, it says cesium iodate here. Well, cesium iodate is not what's given to you. So what kind of reaction is this? Double replacement reaction, we're making precipitate, right? So we actually have 2 things going on. We're like, okay, react these things, make a solid, and then once that solid sits there, what happens to it? Does it dissolve more? Does it make more precipitate? What happens to the equilibrium part? So I'm going to show you the BCE and then the equilibrium reaction, but here's the flow on how to do this. Whenever you have to figure out if a reaction will precipitate, here's your step-by-step. Very first thing you want to do is take your initial concentrations given and take them and dilute them in the bigger volume. So what does that remind you of? Take your initial concentrations, dilute them in the bigger volume. Where have you done that before? Like 3 laps now, right? You're like, multiply volume times molarity, divide by volume total. That gives you your new molarity, your diluted new molarity. Calculate Q and compare it to KSP, and then from there figure out if it precipitates. And if it does, sometimes it'll ask for like, what are the ions left? Sometimes it'll say, hey, does it precipitate or not? So I'll do 2 examples here. So here's your flow. Here we go. You're going to want to write down this one. This is a very good one to make sure you refer back to. So I know that, and actually I'll just say double replacement reaction, because I don't want you to think that that reaction is important. That reaction itself is totally irrelevant. It's just the fact that makes this solid cesium iodate precipitate. I just want you to know that it makes the precipitate. So then from there, very first thing I want you to do, actually I told you the first thing was dilution, so I'll go with that. Take this information, 75 milliliters, and the molarity given, and let's find the moles of that first reactant, and then let's divide by the total volume to get the diluted molarity. So 75, so step 1, dilute. 750 milliliters times 4.0 times 10 to the negative third molar divided by, what's our total volume?
1,050 milliliters.
And so I'm actually leaving it as milliliters here. and molarity, I'm not changing it to millimoles or milliliters, it's because the milliliters will cancel out, right? Leaving me with molarity. So I'm good with molarity here. I'm not, you can change it to liters, it will work exactly the same way. Because this is just a volume ratio. And so this is going to give me the concentration of, you'll notice this is cesium nitrate, cesium-3, or cerulean. What is C?
Cesium.
Cesium? No, CS is cesium.
Oh.
What is CE? I don't even see it. Oh, it's down there. Cerium. Sorry, cerium. Cerium 3 plus is what this is. So this cerium 3 nitrate is just important enough to give me the cerium 3 plus ion. So what is that concentration? Calculate. You just haven't done any calculations today. I'll let you do this one. .02857. So 2.857 times 10 to the negative 3 molar. Yeah. Okay. So this is the important initial concentration of cerium. Same thing for iodate. So iodate was 300 milliliters times its concentration given. 2.00 times 10 to the negative second molar of KO3 over total volume of 1050 milliliters. And so iodate's concentration is 5. You guys are going to have to help that, Alex. Okay, so here's your iodate concentration initial. So after I diluted, you can obviously see the concentrations have decreased just because they're in a bigger volume. What do I do next? What's on our step-by-step here? Okay, so to calculate Q, and we'll compare that to the KSP value of cerium-3 iodate. What is the Q, aka the KSP expression for this one right here? So Q or KSP is equal to
Concentration of
cerium 3 plus
iodate.
Cubed. Yeah. So I do want you to write that out first because you'll forget to cube it. I know you people, you will, because I do. And then from here, we're just going to plug in the values we got from dilution. So 2.85 times 857 times 10 to the negative third molar first power, and then 5.714 times 10 to the negative third molar cubed. I do have, yeah.
So for KSP, are you breaking the products out to the ions?
Yep. And this one, so basically the reaction, the double replacement reaction happened first, right? And that was solely to make this precipitate. But then this precipitate ionizes, as any precipitate does, into its ions, just like we had solid yielding cerium 3 plus and 3 iodates.
So you don't do the reaction with you.
Right, and that's the hard part. Like when I first started learning KSP, I was like, how do you know which one you write the expression for? Well, all of this is regarding equilibrium. So the double replacement reaction makes a ton of products over a ton of reactants. That is not the equilibrium reaction, so it is irrelevant. It's solely there to create a solid. That solid then equilibrates out to its 2 ions, or in this case, a 1-to-3 ratio of its ions. That is when we write the KSP for. So make sure you're just specifically writing it only for the KSP equation. So then when you plug those in, you get, and these are initial values, right? So I'll just put a little I there and I there to represent that. This value is 5.33 times 10 to the negative 10. Okay? Is that value greater or lesser than Q? I mean, than KSP? So you got 5.33 times 10 to the negative 10 versus 1.9 times 10 to the negative 10. Greater? Yes? 5.3 is greater than 1.9 because they're both to the same exponent. So this is greater than KSP. So then you tell me precipitate or ionized still? Because
there's too many ions.
too many ions, right? So you would explain that a bit further. You would say precipitate forms because there's too many ions creating a supersaturated solution. Therefore, it would shift back to the reactants forming more solid. You can string that into a nice phrase for your AP readers, because they're looking for keywords. So, okay. So you got your step-by-step here. This next one is similar. Let me see. Do I want to do this one? Oh yeah, we need to do this one because this one's not. You tell me what's different about this one.
At equilibrium.
So it's asking for what at equilibrium?
The concentration, so you're gonna have to do the exponents.
Yeah, we're looking for X, we're looking for the concentration. So it's not like, oh, let's just compare now. We're going to compare, we're going to do an icebox, we're going to then solve for X. And this one was on, one like this was on the AP exam 2 years ago. So, tell me our first step.
Find the initial concentration.
Okay, let's find the initial concentrations. Can we just talk about the double replacement first? The double replacement reaction is occurring to make what?
Magnesium chloride.
Okay, so we have magnesium fluoride, that's our precipitate, and that's what we're going to be allowing to dissolve into its two ions. So actually, I'll just write that over here really tiny. What does it dissolve into?
Mg2 plus and 2.
2F. And that's just there to remind us that that is the equation that we're using for a KSP. Okay, so the dilutions. Tell me my process, and I'll tell you guys the numbers next, but our process, but tell me the process.
Magnesium, it's 150 milliliters times 177.
Yeah. So this is M times V for the magnesium nitrate divided by the total volume of 250 plus 150, so total volume is 400. So magnesium's concentration initial will be 3.75 times 10 to the negative third molar. And I know it's a lot of writing, but it's really good to label what you're talking about because you'll forget what each of these regard whenever you get down to your math part. All right, so fluorine.
Fluorine is 200 milliliters first.
So they're the same concentration initial. And the misconception that a lot of people will use is like, oh, the initial concentrations are given. I'm going to plug those into ice. Those are not, those are the initial concentrations of the two separate reactants, but when they're together, they have a new initial because they've now been diluted in a larger volume. And that's what the AP reader said, like this question everybody screwed up on. So you guys will be overly prepared. That is 6.25 times 10 to the negative second. Okay, molar. Yeah. Okay. Dilution step. Next step.
Q.
Let's calculate Q. And we're going to compare that to KSP and figure out which way it proceeds, right? So Q, and the expression for this is concentration of magnesium, fluoride squared. Good. And so then we'll plug in values. I'll write out my work. 3.75 times 10 to the negative third times 6.25 times 10 to the negative second squared. So I get Q to be 1.465. I don't mind writing down, doing all the math for you guys as long as you're paying attention and watching what I'm doing here. Okay, so I got Q to be 1.5-ish times 10 to the negative fifth. Compare that to the KSP value. Is it higher? Okay, so this is greater. What is KSP value? Okay, so the KSP value is 6.4 times 10 to the negative 9. So this is greater than KSP of 6.4 times 10 to the negative 9. So which way does it proceed?
Left.
It proceeds left towards the reactants. Okay, so this is where we have to show the setup of an icebox to indicate the shifting of the towards the left side, and then we're going to actually solve for X. So I'm going to rewrite my expression or my equation because it's up there and I can't see it now. So magnesium fluoride equilibrates to magnesium plus 2 fluorines. What am I starting with of both of these? Yes. No. The ones that you've already solved for. The diluted initials are what you're starting with. So that's the point, is like once you've done your dilutions, those are the initials, they go in here. So that's 3.75 times 10 to the negative third, and this is 6.25 times 10 to the negative second. Okay, now what do? Knowing that I'm proceeding left. Where do I put x's and what do I do with them?
Subtract x's from the right.
Good, so if I'm proceeding left, I have to subtract from products and add to reactants. So I'm subtracting what here? On the fluorine? 2x, and I'm subtracting 1x here, and I'm adding x's over here, but those are solids, so I'm not going to really write anything there. It's irrelevant. So we have the number minus x and that number minus 2x. Now what do I do?
You take that and plug it into your K expression.
Good. So you take these equilibriums here and here, you plug it into your K expression, and then maybe we can neglect x, maybe not. Let's talk about it as we get there. So our K expression is the same setup up there, so I'm just going to write KSP is equal to 6.4 times 10 to the negative 9, and that equals magnesium's concentration at equilibrium, which is this stuff, so 3.75 times 10 to the negative third, minus x, times what? 6.25 times 10 to the negative second minus 2x squared, because that's what our original expression was. Okay, so you can see this one's like a 4-part problem. Like this would be like A, B, C, D on the AP exam. What are your thoughts on neglecting x? Would you like to try, or do you think it's going to be not less than 5%? Let's try. Okay, so you'll notice you're subtracting from fairly small numbers, so this x is going to have to be pretty dang small to be less than 5% to be negligible, or you can plug it right in. And I'm going to tell you mentally, I have tried to neglect for x. It's not small enough to neglect. So if we did neglect x, we would negate those to be 0. Actually, no, I lied to you. What happens if you neglect x? If you neglect x, you take that away, what are you solving for? Nothing, right? So then you're probably like, I can't do this neglecting x's. I would be negating the x's I would be solving for. So you can't do it here. Okay, so then how would you solve for x here? What's your new favorite thing?
Solver.
The solver. Please, you can try to plug this in your solver to make sure you got it right, but when you plug this in your solver versus doing the, what do you call the 1 to the third power? Not quadratic formula. Polynomial. The third to the third. So this is where I'm like, please use your solver and do not waste your time. I remember using my solver on my AP exam and having to just double check it like twice just because I was scared I typed something in wrong. So you got x, whenever you use your solver, you get x to be 3.74788 times 10 to the negative third molar. And I've extended that out some so I don't have any rounding error right now. Okay. What was the question again, guys? We've been doing these problems for so long.
Concentration.
It's asking for concentrations, right? So, how do I solve for magnesium's concentration? Right, you take the 3.75 times 10 to the negative third, which is the given for initial, subtract x, and that equals approximately what?
0.
It actually equals a number. Okay, so if you put minus x, I'll know that you're plugging that in. You guys with me? I know that you're plugging that in, and then here you're just literally plugging in your calculator. 2.12 times 10 to the negative 6 molar. So essentially 0, yes, but it is a number. Your stuff dissolved. And then fluorine, you would do 6.25 times 10 to the negative second minus 2x, and that's approximately 5.50 times 10 to the negative second molar. Big breath, pat yourself in the back. That was insane. We did a good job. We did that for way too long. But those are all the types of KSPs that you experience, okay? Instead of, because I was going to have you guys look on the back side of the very last page of the notes. I will assign very few of these just so you have maybe 2 or 3 that you practice independently. So I've taught you, oh gosh, I haven't taught you how to do loss curve 6. How about you guys do 4 and 5A. 5A being the first one, and that's it. I'll wait, I'll do the rest of the stuff tomorrow. I've got a couple, 4 and 5A, and that's it. So 2 questions on KSP. The homework is to prep your lab notebook for your calcium hydroxide KSP lab tomorrow. Find it in your packet. I would recommend, so you guys know I copy packets with no backs on them, so you can cut out the lab procedures and type them in your lab notebook as needed, or just the lab itself, whatever it is, picture and everything. But you should prep that because you'll see the questions embedded, or if you just go there and highlight the questions that are embedded in the lab procedure itself, it'll help guide you. Like, okay, I get to this part, I need to calculate this. I get to this part, I need to calculate this. And then the textbook problems are related to KSP. So try your best. If you don't get to prep your lab, it's just going to take you long in the lab tomorrow, but it depends what you're doing tomorrow. And then if I have to, I can extend lab notes maybe to Monday, but you have a test on Monday. So I don't want you doing your labs all weekend. I'd rather you be studying. So let me know tomorrow how that's going to be, okay? But I want to give you time. I don't want to stress you out, but I don't want you just doing labs over the weekend. So let me know. Okay. All right, get up and move around or do homework. You have 10 minutes-ish, okay? Read over the lab if you want to. Yeah, yes. And Straw, go get your textbook. Oh, yeah, good. Good timing. There you go, Devin. Let me check my schedule.